Hey guys, we are in our last worksheet, the review worksheet for gas laws. This is going to be problems 1 through 5. So if you want the rest, you have to go to a different podcast because this is only problems 1 through 5. Okay, let's get going. All right, as we look at problem 1, we have a balloon that's going up to the top of Mount Everest. So we have some things changing. So that tells me we're going to have to use our combined gas law. P1V1 over T1 equals P2V2 over T2. All right, so what do we know? Well, we've got a 6.2 liter balloon, and we're trying to figure out its size or its volume. So we're trying to figure out how many liters are at the end. We have some temperatures here, 55 and negative 35. So let's go ahead and convert those to Kelvin, because we always know that our temperatures must be in Kelvin. So we have to add 273 to 55 and 273 to negative 35. That's pretty poor, isn't it? Negative 35. There we go, plus 273. Right? And our two temperatures are going to be 328 Kelvin. And then when we get up to the top, they're going to be 238 Kelvin. Okay, and let's see, we've got millimeters of mercury and millimeters of mercury, so we don't have to change anything there. Remember, the units don't matter so long as we're consistent. Okay, so let's go ahead and work this one out. We've got our initial pressure is 615 millimeters of mercury, and our initial volume is 6.2 liters, and our initial temperature is 328 Kelvin. And our final pressure is, let's see, 400 millimeters of mercury. Our final volume is what we don't know. And our final temperature is 238 Kelvin. So we're going to cross multiply. We're going to multiply these things, and then we'll divide by what's left. So we get 615 millimeters of mercury times 6.2 liters times 238 Kelvin, and we divide by 328 Kelvin, and we divide by 400 millimeters of mercury. And we just make sure, because our units cancel, millimeters of mercury and Kelvin cancel, we're left with liters, which is what we want. And our final answer here, when we do the math, is 6.9 liters is our final volume, and we have 6.9 liters, only 2 sig figs, because we've got only 2 sig figs up the top of our problem. All right, let's go on to number 2. We have 2.5 grams of oxygen, 56 degrees Celsius, 45.3 atmospheres. What's the volume? I like my volumes in liters, so I'm going to use PIVNERT. PV equals nRT, and I want to solve for volume, so volume is going to be equal to nRT over V over P. All right, now, obviously my Celsius temperature needs to be converted. So 56 degrees Celsius plus 273, and that's going to give us 329 Kelvin. And we have 45.3 atmospheres, don't need to convert that at all. We do have to worry about our oxygen, though. We've got 2.5 grams, so we have to figure out the molar mass of oxygen, which is 32 grams. You should be able to figure that out. So we have 2.5 grams of oxygen, and we have to convert that to moles of oxygen, because we need moles right here. So we take 2.5 grams of oxygen, and we have 32 grams of oxygen in 1 mole of oxygen. So when we do that math, we come up with 0.078125, and that's moles of O2. And so now we can actually use our PIVNERT formula, solve for volume, which is equal to the number of moles, which is 0.078125 moles. Now we have to multiply that by R, which is 0.0821, liters, atmospheres, moles, Kelvin. And we have to multiply by our Kelvin temperature, which is 329 Kelvin. And we have to divide by pressure, and our pressure is 45.3 atmospheres. And let's see, my atmospheres cancel, my moles cancel, my Kelvin cancels, so I'm left with liters, which is what I would expect to have for volume. So my volume is going to be 0.047 liters. And for O2. And why only 2 sig figs? Well, because I've only got 2 sig figs in my problem. So that all makes sense. All right. We've got some sodium carbonate. It's reacting with hydrochloric acid to make water, carbon dioxide, and sodium chloride. Clearly, what I'm going to have to do here is come up with a balanced chemical equation. So I have sodium carbonate, CO3, is reacted with hydrochloric acid, that's HCl, to make water, which is H2O, and carbon dioxide, which is CO2, and sodium chloride, which is NaCl. Let's look at this. Remember, Na is +1, chlorine's -1, so that's good. Carbon dioxide and water we don't worry about. Hydrochloric acid +1, -1. Sodium carbonate +1, -2. So that means I'm going to need 2 sodiums here. So since I need 2 sodiums, that means I need to have 2 NaCl's, which means I need to have 2 here, and I am now balanced. Okay. So I'm also collecting gas over water at 24 Celsius. So let's figure that out. 24 Celsius is 22.3 if I look at my water vapor table. So I need to take my 615 millimeters of mercury, 615 millimeters of mercury, which is my total pressure, and I have to subtract from that, I already forgot what it was, 22.3. 22.3 millimeters of mercury, and this is our water vapor pressure. Right? And so when I subtract those two, I get 592.7 millimeters of mercury. And this is the vapor pressure of the CO2. Because it's talking about a gas, well, the only gas we have over here is CO2. Water is a liquid, sodium chloride is a solid. It's actually going to be aqueous in this point. So definitely CO2. All right. And let's see, we want to figure out volume of gas produced. So to figure out what volume of gas to produce, I need to first figure out how many moles of the gas is produced. So I have to figure out how much sodium carbonate weighs. So I take 2 sodiums, which are 22.99 each, plus 12 for carbon, 12.011, plus 48 for oxygen. So my molar mass of sodium carbonate is going to be 105.99 grams per mole. All right. So now I can convert my 23.5 grams of sodium carbonate into moles of sodium carbonate by getting rid of the molar mass. 105.99 grams of sodium carbonate in 1 mole of sodium carbonate. And then I have to go from moles of sodium carbonate to moles of CO2. And let's see, I have 1 mole of CO2 over here, and I've got 1 mole of sodium carbonate over there, so they'll cancel each other out. All right, so I do the math here, and I get 0.2217 moles of CO2. All right, well now, what I can do is I can go back and I can do PivNert. Right? But my problem is to do PivNert, I want my answer in liters, and I've got 615 millimeters of mercury that needs to be in ATMs because I need to match my R constant. So I need to convert 615 millimeters of mercury into ATMs, which I do by 760 millimeters of mercury in 1 ATM. Right, so I go and I divide that, and I come up, well, wait a minute, that's not right. Nope, can't do that. Wrong. I have to take the 592.7 because I only want to do carbon dioxide. So let's try that again. 592.7 millimeters of mercury. And I convert that, 60 millimeters of mercury, into ATMs. And that number is going to be 0.779868. If you've watched any of these, you'll know that I use a lot more significant figures here than I'm allowed, just to make sure I don't get rounding error over and over and over again. I'm only going to have 3 sig figs in my answer, but I might as well carry some along the way. All right, so if I do PivNert, and I'm trying to calculate volume, that means volume is equal to nRT over P. So my volume is going to be N, which is my number of moles, which I have up here as 2217. So so 0.2217 moles. And my R constant is 0.0821, and that's liters, atmospheres, moles Kelvin. And my temperature is going to be, where's my temperature? 24 Celsius. Oh, I never converted to 24 Celsius, did I? So I have to add 273. Where can I do this? All the way at the top. How's that? 24 plus 273 gives me 297 Kelvin. Okay, so my temperature down here is going to be 297 Kelvin. And I'm dividing that by my pressure, and my pressure in atmospheres is 0.779868, and that's atmospheres. Now, I check my units to make sure that I'm getting rid of things. I've got atmospheres in 2 places. I've got Kelvin in 2 places. Moles in 2 places. What I'm left with is liters, which is what I want for volume. So my final answer here is going to be 6.94 liters of CO2. And that's my answer to number 3. All right, let's go on and look at number 4. Number 4, we have a bicycle tire with a certain volume. You'll notice what's happening is the volume isn't changing. But if you think about this problem before you jump in and start doing numbers, and again, I'm trying to get you to think about these things, right? If you remember, we did PV equals nRT when I did my showing you how this was derived, and we took PV over NT is equal to R. And so this can be the starting system, and since your R constant never changes, you could have P2V2 over N2T2 as another possibility. Now, typically we don't have moles in here because our moles remain constant, but in this case, we're doubling the number of moles. Well, if you look at this, what we're doing is we're looking at the pressure and the number of moles. We're assuming the volume remains constant. So since the volume remains constant, we don't need it on either side. And we're assuming the temperature remains constant, so that's going away. So all we're left with is P1 over N1 equals P2 over N2. So what happens if, when I go from N1 to N2, I double the value of N2? Well, then I better double the value of P2 to keep the ratio the same. Because if this is 1 and 1, and I make the number of moles over here 2, then the only way to keep a 1-to-1 ratio, or 1 over 1, is to make this 2 over 2. So it had to double. So without doing a whole lot of math, I have demonstrated they double. Now, if you want to go and work out a problem, you can work out a problem, but you really don't need to for this particular problem. All right, this is the last one we're doing on this podcast, number 5. It says we have hydrogen peroxide and it's decomposing. So let's write down hydrogen peroxide decomposing. We have H2O2 decomposing into H2O plus O2. We notice we have 3 O's over here. We need an even number of O's, so I put a 2 there and a 2 there. All right, so we have 2 hydrogen peroxides, 2 waters, and 1 oxygen. Okay. Let's see. We're saying it forms water. How many grams of hydrogen? So we're looking at grams of hydrogen peroxide. Okay, so that means we're going to have to figure out the molar mass. So let's do that right now. The molar mass of hydrogen peroxide is H2O2. That's 1.0079 times 2 plus 16 times 2. Okay, so that gives you 34.016 grams per mole. All right, we're going to need that later. All right, let's see. We're looking at 324 milliliters of oxygen. So we know that that is 0.324 liters. Right? Don't need to do a lot of math there. We're talking about collecting it over water at 18 degrees Celsius. All right, so let's look at 18 degrees Celsius. If we look at 18 degrees Celsius, that's a pressure of 15.5 millimeters of mercury. And we notice that we're starting with 685 millimeters of mercury. So let's take 685 millimeters of mercury and subtract 15.5 millimeters of mercury. And that's going to give us 669.5 millimeters of mercury. Now remember why we did this. This is going to be our pressure of oxygen, and this is going to be millimeters of mercury This is going to be our water vapor pressure. Right, and this is our total pressure. Remember, this is Dalton's law that we learned about. All right, we have 18 degrees Celsius. We're going to have to take 18 degrees Celsius and add 273 to that, because we need to always have our temperature in Kelvin, which is 291 Kelvin. All right, so let's see what we need to do. We're collecting a bunch of oxygen, so we have to figure out how many moles of oxygen this is. So that means we're going to have to use Pivner to figure out moles of oxygen. So let's see, PV equals nRT. That means the number of moles is equal to PV over RT. All right, so our pressure needs to be in atmospheres. Oops, so we haven't done that. Let's go ahead and do that. We have 680. No. We have to use this pressure down here for oxygen. So we have 669.5 millimeters of mercury. And we have to convert that by putting 760 millimeters of mercury down the bottom and 1 atmosphere on top. We've done a lot of these. Right, so you should be pretty familiar and comfortable with these. And that's going to give us 0.88091 atmospheres. All right, so let's see. Our pressure is 0.880921 atmospheres. Our volume is 0.324 liters. Remember, we had to do liters instead of milliliters because of our R constant, which is 0.0821, and that's liters, moles, Kelvin, liters, atmospheres, moles, Kelvin. And we have to put our temperature on the bottom, which is Kelvin, which is going to be 291. That way we can cancel liters, moles, and liters, Kelvin, and our volume to come back with number of moles. So when we do that math out, we get this mess. When you go and do the math, right, you come up with 0.011946664 moles of oxygen. Well, now I have to go and use my stoichiometry to get from moles of oxygen to moles of hydrogen peroxide. So I'm starting with 0.011946664 moles of oxygen. And I'm converting from moles of oxygen to moles of H2O2, or hydrogen peroxide. And it asked me how many grams of hydrogen peroxide decomposed. So I have to get rid of moles of hydrogen peroxide and go to grams of hydrogen peroxide. All right, well, I figured out my molar mass up here of hydrogen peroxide, which was 34.016 grams per mole. And I can tell that 1 mole of oxygen gives me 2 moles of hydrogen peroxide. 1 mole gives me 2 moles of hydrogen peroxide. So I do the math out here, and I get 0.813 grams of hydrogen peroxide. All right, guys, that's a lot of work. That's the most complicated thing you're going to see from us. But that's the way you work it out. Okay, that was number 5. If you want the rest, you've got to go to the next podcast. That's it for this one. Have a great day. If you have questions in class, please let us know. We'll be more than happy to help. Okay, see you soon. Bye-bye.